Alrighty, folks. Well, we finished up Unit 1, done. So you know what that means. We are now on to Unit 2, Polynomials, Radicals, and Rational. Polynomial, radical, and rational functions, mostly, is what we're going to be looking at. As with most of the units, it's kind of broken up into two topics. We'll spend a little more time on polynomials. You can think of that as topic 1. That's what we're starting in this lesson here. And then we'll move into radicals and rationals. That's kind of part 2 of this unit. So in this first lesson here, we're going to take a look at some, just getting to know polynomial functions a bit, and then also look at how to work with them in terms of dividing. That'll be a skill that is important for us as we continue into working with polynomial functions more, eventually wanting to factor them in order to find solutions or x-intercepts or otherwise analyze them. Okay? So as always, there's kind of the checklist for the big ideas, the key skills that we're hoping to take away after this lesson. Use it to check in with yourself afterwards. So let's jump right in. All right, so you've worked a ton with polynomials in, just about every math course you've taken in high school. Polynomials come up, you talk about them, but let's just remind ourselves the terminology and stuff, because we're gonna rely on referring to these things with their proper vocabulary. So what is a polynomial? Remind ourselves of that before we start talking about polynomial functions. All a polynomial is an expression that's made up of one or more terms, right? It's got one term, we usually call it a monomial, 2 terms, a binomial, 3 terms, a trinomial, and on and on and on, right? So with the terms, what constitutes a term? Sometimes students are a little thrown off. They say, is this the term and that's a term and that's a term? No, the terms are separated by addition or subtraction. So taking a look at this example here, okay, we've got 3 terms. We've got a 3x squared term plus a 4x, that's our second term, plus a 1, that's the third term. So this would be a trinomial, tri meaning 3, like a tricycle or a triangle, right? Okay, so each within those terms, right, each term consists of coefficients and variables, and the variables will have an exponent on them for a polynomial. Okay, so if we take a look, again, we've got our 3 terms, and then within the term, we can break it down to the parts of the term, okay? So there's the variable, often x, of course it doesn't always have to be, right? But that's a common one. We've got our x, the coefficient is the number that's being multiplied by our x, right? So this has a coefficient of 3, this has a coefficient of 4. The variable is x in both cases. Okay, and then there's an exponent on our variable in this term here. We've got our 3x squared term, so the exponent on the variable here is 2x squared, okay? The exponent on the variable here is 1. We don't usually write a 1 in, but it wouldn't be wrong to say x to the power of 1, okay? And even here, this is what we would call our constant term. Why constant? Because it doesn't change if the variable changes, right? This is just 1. There's no x attached to it. But even that term, even the constant term, obviously we often don't write it in because it's just, being a little extra for no reason, okay? But we could we could think of this as having an x to the power of 0 term, because anything to the power of 0 is just 1. Okay, so even the constant term, in a sense, it does have a coefficient, a variable, and exponent. It's just that the exponent on the variable is 0, so it ends up just being just a number, right? The constant is just a good old number. Constant because it's not going to change when x changes. Okay, so as we said, any letter can be used as the variable. The most common is definitely x, but, don't get thrown off if it's a p or an n or something like that, okay? In a polynomial, here is one of the key things to get into the polynomial club. You can only have exponents on x that are whole numbers. Okay, so notice here we've got x squared. We could call this x to the 1. And as we said, we could even call this x to the power of 0. But you do not see x to the power of 1/2 or x to the power of -5, right? It's the whole numbers. Remember, whole numbers are just the non-negative integers. So that's 0, 1, 2, 3, 4, 5, 100, right? But not 1.2 or 3.5, right? Whole numbers. So fraction, decimal, or negative exponents will not be found on the variable in any terms of a polynomial expression. If it does have that, well, then it's not a polynomial, right? If we see something like 4x to the 1/2 plus 3x. I mean, there's nothing like illegal about this, but it isn't a polynomial, okay? Same goes if we had like 3x to the minus 2 plus 2x squared, or something like that, right? That minus 2 means we don't have a polynomial here, okay? It's an expression, it's a mathematical expression, and we could talk about it, but it is not classified as a polynomial. For a polynomial, you can only have whole number exponents on the variable. And just a reminder, that means, what these exponents mean, you might recall x to the power of 1/2. This is equivalent to 4 times the square root of x, right? X to the power of 1/2 is actually the square root of x. If you need some reminding of why that's true, think about this. X to the power of 1/2 times x to the power of 1/2. We know that these have the same base, so we can actually just add their exponents, right? That's one of our exponent laws. So 1/2 plus 1/2 is 1. So that just means that whatever x to the power of 1/2 is, it's the thing that when you multiply it by itself gives you an answer of x. Well, hey, that's just the definition of the square root of a number, right? If we multiply the square root of 4 by itself, we get 4. Well, the square root of 4 is 2, and 2 times 2 is 4, okay? So a fractional exponent means we're dealing with a root. X to the power of 1/3 is just the cube root of x, for example, okay? So sometimes it might not, you might see a root x and wonder, is this a polynomial? No, it's not, because that means we have a fraction exponent on our x, okay? Also, the negative exponent, do you remember that x to the negative 1 really means 1 over x, right? X to the negative 2 really means 1 over x squared. Again, that comes from our exponent laws and the fact that we could think of like, x times x over x times x times x, x squared over x cubed, cancel those all out, x squared over x cubed, subtract those exponents, x to the minus 1, right? Because again, each division by x is like removing an x here. X over x is just 1, x over x is just 1, and look what we were left with. Just a 1 in the numerator over x. Quick reminder of some of that exponent law stuff, okay? But again, just to emphasize the point that this would not be considered a polynomial, 1 over x, right? 2x plus 3 over x, for example, is not a polynomial because that x has a negative exponent. Polynomials can only have whole number exponents. So no variables in a root or a denominator. X squared, x cubed, x to the power of 12, all of those are okay for it to still be a polynomial. So what is a polynomial function then? I mean, it's just a function where the equation for that function is a polynomial, right? I mean, that's probably not too shocking. If I were to go to this and I would just say f of x equals this stuff, there we go. Now it's a polynomial function, right? If I say y equals that, I've written out a function. So a polynomial function is just a function with the equation of a polynomial. In other words, we're going to input x's into a polynomial function or polynomial equation, and then it spits out the corresponding y values. You've studied tons of polynomial functions, right? You saw linear and quadratic functions in Math 10C and Math 20-1. Guess what? Those are polynomial functions, right? A quadratic expression is a polynomial, right? Same goes for a linear expression. It's a polynomial. Notice this passes all the tests to be a polynomial. Only whole number exponents on our variable x, right? X to the power of 1, x to the power of 2, x to the power of 1, x to the power of 0, okay? And it's got multiple terms separated by addition or subtraction. That's it. It's a polynomial. No root x's, no 1 over x's, or anything like that. So in a linear function, the greatest exponent on x was just 1. That makes it a linear function, right? 1, exponent of 1. In a quadratic, really, it's still just a polynomial, except now we introduce x squared terms. So the greatest exponent on x is 2. So all we're going to do here, folks, in Math 30 is go beyond that. So you've seen polynomials with a greatest exponent of 1, polynomials with the greatest exponent of 2. Guess what? We're just going to go higher than that. We're going to go up to 5. Okay, so now we're just going to study polynomials with exponents greater than 2, up to 5. Could you go beyond 5? Totally. Honestly, none of the stuff we're going to talk about changes. That's just where the Math 30-1 curriculum decided to stop it. They said have students study up to greatest exponent of 5 on x. Okay, so just a note on forms here. Okay, what we often want to write polynomials as, it's one of those things where it's kind of just like proper etiquette almost for math, and you'll see why. Like, it is nice to have it in this form. It lets you pick out the important information quickly. It's what we call standard form. And all standard form is ordering the terms from the greatest exponent on x to the smallest exponent on x, right? One of the reasons that's really nice is that the first term then is the largest term, and that tells us a lot about how the function's going to behave when x gets really large or really small, because that's the biggest power of x, so it kind of dominates the behavior of the function since it'll be the largest, having the largest exponent on x. So in general, this is going to look a little intimidating at first. I promise it's really not saying anything too scary, okay? A polynomial function in standard form, we write it like this, okay? This is just a very general way to write a polynomial. I know it looks a bit intimidating, but all it's showing us, look, here's a term, plus another term, plus another term, plus another term, however many terms we have in between, up until the last term, our constant term, okay? And each term, all it's saying is that it'll have some coefficient. Those are our a's here. So our first one they're calling an, right? Then another term will have another coefficient. They're just calling that an minus 1. Just saying if this is like the largest power on x, right? This is the second largest power on x. This is the third largest, all the way down to the smallest power on x, okay? And notice they're all just multiplied by the variable, that's our x's, which is then raised to some power, the n minus 1. So this is standard form because you can see if x to the power of n, if n is our largest exponent, this is the next largest, the next largest, squared to the power of 1 to the power of 0, and that's our constant term, right? So all it's showing is that in standard form, we will write out our terms from the highest exponent on x all the way down to the constant term, which is an exponent on x of 0, okay? The terms are ordered from the highest power to the lowest power, from n down to 0, okay? So all this is a general form. This is saying the same thing, it's just got actual numbers in, right? Here's an example using actual numbers. It's saying what this is generally describing, okay? So you could have 2x to the power of 5 plus 8x to the power of 4 minus x cubed plus 10x squared minus 4x plus 8, right? This is an example of a what we'll eventually call a fifth degree polynomial in standard form. You can see it's in standard form because it goes from the highest power on x to the lowest power on x, the constant term, x to the 0, okay? An important note here, not every polynomial is going to have every power of x represented though, okay? Even in standard form, right, it's not always going to go from 5 to 4 to 3 to 2 to 1 to 0. It will go from the highest power on x to the lowest power on x, but some of those coefficients could be 0, and so you won't always see every power represented from the highest down to the lowest, right? So for example here, the coefficients on the x cubed and the x term are just 0, right? It's still in standard form, because it goes negative 3x to the 4th power plus 1/3 x squared plus 10, right? It's written in decreasing powers of x, okay? But the x cubed, there's no x cubed term and no x in this, right? You could think of this as being equivalent to negative 3x to the power of 4 plus 0 x cubed, right? No x cubed term in this one, plus 1/3 x squared plus 0 x plus 10, right? That's kind of, if you wanted to show every power, right, that's kind of what's going on here. It is a polynomial. It is in standard form from highest power of x to lowest. It just doesn't happen to have an x cubed or an x term. All right. All right, let's get into one of the first important terms that we're going to use when we're describing polynomial functions, and one of those things that's going to tell us about the behavior of the graph of the polynomial function in an important way as well. Okay, so first up is something called the degree, and all the degree is the highest exponent on x. That's really all there is to it. So for example, f of x equals x cubed minus 4x plus 1. That has a degree of 3. Why? Because the highest exponent on x is 3. Right? Take a look at this one. Now be careful, right? There's never any promise that they're going to give it to you in standard form. So in standard form, we would, expect this to be the highest exponent on x, but this isn't written in standard form, right? We'd have to rearrange these terms. Notice The highest exponent on x, if we check each term, is actually 5, right? So this one wasn't written in standard form. We'd probably want to rewrite it in standard form before, continuing on with it too much, just to make sure we don't miss anything. Okay, but that has a degree of 5. It's the greatest exponent on x. The second important term that we're going to use that's going to tell us about the behavior of a polynomial function is the coefficient, the number attached to the variable, you could call it, but we know that really just means a coefficient, right? The number attached to the variable with the largest exponent is called the leading coefficient. So taking a look here, we identified that the greatest exponent on x was 3. So the coefficient of this term would be our leading coefficient. So in this case, this example here, it's just 1, right? This has a coefficient of 1. We often don't write in that 1 because 1x cubed is the same as just x cubed, but that would be its leading coefficient, 1. What would be the leading coefficient in this one? Can you pick it out? It would be 4. Good, right? Careful, not 2. This isn't written in standard form, right? Obviously, anything could be in the lead position if we rewrite it however we want. But the leading coefficient is based on, in standard form, it would be the first term. It would be in the lead position, right? When written in standard form, that will be the first term because we put the highest exponent first in standard form. But either way, this is still called the leading coefficient. It's the coefficient for the term with the greatest power of x, okay? So for your quadratics, right? Quadratics have a degree. Let's put that new terminology to the test. What would be the degree of a quadratic function? 2, right? The greatest exponent on x is 2. What would be the degree of a linear function? 1. The greatest exponent on x is 1. Very good. Okay, what would be the leading coefficient of this function? -3. You got it, right? The coefficient for the term with the greatest exponent on x, right? Leading coefficient 1. Leading coefficient 2/3 for this one. Leading coefficient 1 for that one, okay? And one of the other things we'll talk about here is the importance of the constant term. Mostly, what can the constant term tell us just by looking at the equation, okay? What it's going to tell us is the y-intercept of the function. Now, that's not some magic rule to memorize. It actually makes a ton of sense because to find the y-intercept, what do? We set x equal to 0 in the equation. And again, that's not some weird trick. It makes sense because where is the y-intercept? It's where the graph crosses the y-axis. And what is the value of x at the y-axis? It's 0. So again, a function, all it does is it tells us what y is when we put in an x. At certain x's, it can tell us what the value of y would be. So if we want to know what is y when x is 0, in other words, what is the y-intercept, we would plug in 0 to these functions, right? And the only term that's not going to become 0 when we put 0 in for x is the constant term, because it doesn't change for what x is, right? If I put in a 0 to this function, I'm going to have 0 cubed, 0, minus 4 times 0, so 0, plus 1. So I'll have 0 minus 0 plus 1, right? Same thing here. This doesn't have a constant term, or rather, it does have a constant term, but its constant term we could just think of as 0, right? Plus 0, okay? All of these become 0 if I put in 0 for x, and I'd just be left with my constant term. You can see that's the case for every one we've looked at, right? Put in 0 for x, all you're going to be left with is your constant term. And so that's why, by looking at the constant term, we can pick out the y-intercept, just by looking at it. Because at the y-intercept, every other term becomes 0, since x is 0 there. Okay, so in standard form, it doesn't even have to be in standard form actually, but it will always be found at our constant term. The term that's just a number with no x attached. Again, we could think of that as having an exponent of 0 on x, because x to the power of 0 is just 1. But there we go. Okay, let's try putting this to the test here with an example. Can we use the degree, the leading coefficient, and the constant term to pick out some features of the graph? All right, so let's take a look here. For the following polynomial functions, rewrite them in standard form. Okay, we'll do that first. Then determine the degree, the leading coefficient, and the y-intercept. So really just picking out the information about the equation. I think I said we'd be telling stuff about the graph. We will do that, but for now, just, getting used to that vocabulary of degree, leading coefficient, and y-intercept and all that. So for this one, definitely not in standard form, right? Look, we can see that the greatest exponent on x is 6. So we need to reorder this thing so that it goes from highest coefficient to, highest exponent on x to lowest exponent on x. So let's put that, we'll rewrite it in standard form. So in standard form, we would have p of x equals 3x to the 6th. It looks like the next highest one is this x to the 5th power, so a negative x to the 5th term. Then we've got that x to the 4th, so minus x to the 4th. And finally, a positive 9x squared, right? And there we go. We've rewritten it in standard form. So what is the degree of this? Looks like the degree, I mean, we could have picked it out even without writing it in standard form, but our degree is going to be 6. Degree 6. We could call this a 6th degree polynomial function. That's sometimes how we word it. Okay. What's our leading coefficient now, right? The leading coefficient is going to be 3. I mean, that was always our leading coefficient, but we call it the leading coefficient, the leading one, because when we write it in standard form, it's in that lead position, right? It's the first one. So our leading coefficient is 3. Leading coefficient is 3, positive 3. And what else did they want us to get? Oh, the y-intercept. Okay, y-intercept here. We know that the y-intercept comes from when we have a constant term, right? That's a quick way to just spot it. Our constant term here, I mean, we kind of have a constant term. It's just 0, right? We could think of it as, all of this plus 0. So our y-intercept is going to be 0. And we can tell that, I mean, it's not just about looking at the constant term. The reason the constant term will be the y-intercept is that if we put in 0 for x, which is the value of x at any y-intercept, right, we can figure out what y would be, right? Y is equal to this stuff. So put in 0 for x and you'll figure out what y is when x is 0. Well, we can see here, if we put in 0 for x, I'm going to have 0 minus 0 minus 0 plus 0. So 0, right? So there we go. There's our degree, our leading coefficient, and our y-intercept, just by looking at the equation. All right, now this one, definitely not in standard form, right? Looks like it's in factored form. So let's go ahead first. If we're going to write this in standard form, we need to see all of our terms, right? All of our terms laid out for us to work with. So before we do anything, we're going to have to expand this. Let's multiply that 8x by those two terms in the brackets there. So 8x times 3, that's going to be 24x. 8x times negative x, that's negative 8x squared. X times x is x squared. Okay. And now let's rewrite it in standard form. So standard form will be highest power on x first. Looks like the highest exponent on our x is just 2. This is just a quadratic. So negative 8x squared, and then a positive 24x, so plus 24x. There we go. That's in standard form. So help me out here. What's the degree? Greatest exponent on x, right? So our degree is 2. The highest power on x is just 2. Okay, our leading coefficient, I'm just going to write LC for short. Well, that's the coefficient on the term with the highest exponent on x, right? So for us here, it's negative 8. Okay, and y-intercept, once again, right, it would be 0. If I put in 0 for x, I get 0, 0 here, 0 plus 0 is still 0. And we could say that's the constant term, but our constant term here is just 0. In other words, we don't really have a constant term, or it's just 0. There we go. So picking out those characteristics of a polynomial equation: degree, leading coefficient, y-intercept, and where we get them from. We want to be comfortable with those because of what we're going to start looking at next, what those tell us about the graph of the polynomial function. Alrighty, folks. So now that we got that down, the idea of degree, leading coefficient, let's just take a look here, take a little tour. As we mentioned, right, we've seen polynomial functions before, right? In Math 10, we looked at linear functions as well as constant functions. Then in Math 20, we added quadratic functions into our toolkit, or our area of comfort, right? All we're doing in Math 30 now, really, is extending beyond that and starting to analyze and look at functions that go above a degree of 2. So beyond quadratics, okay? So first things first, let's just get to know the names of these a little bit, okay? If we have a degree 3, we call it a cubic function. Means the highest power on x is 3, right? Which actually makes sense because we would call that x cubed, hence the name cubic function. Quartic, like quarter, fourth, right? A 4. So a quartic function has x to the power of 4. A quintic function, like quintuple, right, has x to the power of 5, a degree of 5, okay? And that's the highest we'll go in Math 30. Again, there's no reason we really have to stop there. Technically, all the skills we're going to talk about could be applied to degree 6, 7, 8, 9. They just had to stop it somewhere, so they said, okay, let's stop the curriculum at degree 5, okay? Now, if we take a look here, okay, one of the first things we're going to talk about with these is the possible number of x-intercepts, okay? The possible number of x-intercepts. You can see that's listed for each of these here, okay? So for a constant function, that's just something like y equals 3, y equals 6, y equals -10, right? A constant function that the greatest power, the highest exponent on x is actually 0, right? We just have y equals some constant. For those, they're not going to have an x-intercept. They're going to have 0 x-intercepts. There is one exception. That would be the constant function y equals 0. Technically, that has infinitely many x-intercepts because that would just be, if I were to draw the function y equals 0, it would just look like that. So technically, everywhere that has an x-intercept, it has infinitely many, okay? Moving on, though, to degree 1, our linear functions, these are lines, right? They're going to have one x-intercept, right? Assuming the highest power on x is just 1, okay? If you think about it, there's no way to draw a line anywhere where it's not going to cross the x-axis once, right? And exactly once, because it's a line, right? So it's going to cross it, and then it's headed that way forever. It's never going to cross it again, right? No matter how you draw one line, it's eventually going to cross the x-axis, and it's never going to turn around and cross it again. So it'll have one x-intercept, exactly one x-intercept. Now we're going to get into, slightly more interesting maybe, or more cases to think about, and that would be for quadratic functions. We saw these in Math 20. Okay, so greatest power on x is 2. We have an x squared term. Okay, might have an x term, might have a constant term, or might not, but we'll definitely have at least an x squared term if it's classified as a quadratic equation. Now, this could have no x-intercepts, one x-intercept, or two x-intercepts, okay? Notice, highest exponent on x is 2. It could have 0, 1, or 2 x-intercepts. Now, this actually makes a ton of sense when we think about it. Again, this is just showing one example, but what would a quadratic with 0 x-intercepts look like? How about something like that, right? Maybe a parabola that opens upwards that's been shifted upwards, or maybe one that opens downwards that's been shifted downwards, right? Those are parabolas. Those are the graphs of a quadratic function, and those would have 0 x-intercepts, right? How could a quadratic have one x-intercept? Well, how about good old y equals x squared? This isn't actually a very good drawing of y equals x squared because it's not passing through the right places, but just a parabola that touches, is tangent to the x-axis, but doesn't actually fully cross in there, right? It has one x-intercept right at its vertex, right? We could show another example of one over here. Could have one x-intercept, okay? And, of course, it could have two x-intercepts, right? That just looks like this, two x-intercepts. So maybe it opens upwards and its vertex is below the x-axis, so that in two places it crosses, or it could open downwards and its vertex is above the x-axis, so that in two places it crosses the x-axis, two x-intercepts, okay? Now again, it actually makes a ton of sense that we could have, again, 0, 1, or 2, graphically thinking about it, and it makes sense that the maximum number of x-intercepts would be 2, right? A quadratic, the graph of a quadratic is essentially going to change directions once, right? So all it can ever really do is cross, change directions, and then possibly cross again. But this is never going to change directions a third time. We know that's not the graph we get for a quadratic. Another helpful way to think about this, why the maximum number of x-intercepts would be 2, is think about factoring a quadratic, right? When we factor a quadratic, we know from Math 20 that we can get stuff like, x plus m times x plus n. Does it always look like exactly like that? No, but we know we can get like up to 2 factors, right? Which means there's basically up to 2 ways to make it equal 0. Again, there's ways where there's only one way to make it 0. Maybe it only has one factor. Maybe it's, x plus 1 squared. That only has one factor. The only way to make this 0 would be to make x equal -1. So 1 x-intercept, right? And there's even ways, again, to make it have no x-intercepts. How about x squared plus 1? That will never equal 0 because x squared is always going to be positive no matter what x is, and then adding 1 to it. So this is always going to be greater than 0, okay? But just to show, if we think about it, we could factor this out, potentially get 2 factors, and maybe there's one way to make each factor 0, but there's never going to be a third factor here, right? If there's another x here, this is no longer a quadratic. It no longer has a degree of 2. Because if I FOILed this all out, multiplied it all out, I wouldn't end up with the greatest power being x. It would be x cubed, right? I'd have an x times an x is an x squared, and then times another x would be an x cubed. So that's why if it's going to be a quadratic function, it's going to have at most 2 unique factors, and therefore at most 2 unique ways to make y equal 0, right, from those factors. Okay, so moving into cubic, similar logic here. The number of x-intercepts is going to be either 1, 2, or 3. Notice 0 is not an option here. Cubics, their arms go in either direction, right? One goes up, one goes down. We'll talk more about that arm direction here in a moment, okay? But because of that, because they have that odd degree there, they're always going to have to cross the x-axis once, right? Now, it's possible they could go like, they could only cross once. Maybe they do something like this, or, like this. That's possible. Those would have 1 x-intercept, okay? 1 x-intercept, 1 x-intercept. But they could also have 2 x-intercepts. That might look something like, 1, and then maybe they just touch, and then they turn around and change direction again. We'll see stuff like that as we go. We're kind of just, I know we're not going too deep into it, just introducing the different things we can see, okay? But again, because of the fact that one arm goes upward and one arm goes downward, much like a linear function, it's going to have to cross the x-axis at least once, right? I mean, for linear, it's exactly once. But for cubic, at least once it's going to have to cross the x-axis and therefore have an x-intercept. It's not possible for it to never cross the x-axis. But it can do it once, twice, or 3 times like we see there, okay? And again, why is 3 the maximum? Why can't it cross 4 times? I mean, we can look at the shape of the graph, but we can also think that if we were to factor, to look for the zeros of this, right? That's often why we factor. We want to find the zeros. If I were to factor some cubic function, I could maybe have, x plus a, x plus b, x plus c. So that's at most 3 different ways to make y equal 0, right? I could make x negative a, I could make it negative b, or I could make it negative c. And that's where I would find 3 x-intercepts. But if there were another factor there, if there were x plus d, well, guess what? This is no longer a cubic, is it? Right? So this would give it a 4th x-intercept. There would be a 4th different way to make the function 0. But now it's not a cubic function because x times x is x squared, times x again is x cubed, times x again is x to the 4th. So that would no longer be a cubic function, okay? So a cubic can have 1 x-intercept, 2 x-intercepts, or 3 x-intercepts. We will talk about why it makes sense that the arms go in opposite direction for these in a moment, okay? Quartic function, kind of a funky looking one, isn't it? It's almost like a parabola with an extra bend in it, so to speak, okay? Now quartic, degree 4, that's an even exponent, okay, even degree, and this could have 0, 1, 2, 3, or 4. So notice, you might start to see a pattern happening here, right? Degree 0 would have 0 x-intercepts. Degree 1 would have 1. Degree 2 could have up to 2, 0, 1, or 2. Degree 3 could have up to 3, not including 0 though, 1, 2, or 3. Degree 4 could have up to 4, including 0, 0, 1, 2, 3, 4. You can even look ahead a bit there. Degree 5 could have up to 5, 1, 2, 3, 4, or 5. Okay? Degree 4, again, how could it have 0? Well, again, because these arms go in opposite directions, or sorry, the same direction for this thing, right? Maybe, that could happen. Almost like a parabola that's been shifted up, but it's not a parabola because it's coming from a quartic function. Parabolas are for quadratics, right? How could it have one? Couple ways you could get one. Whoops, not like that though. One could come from, this. Touches once, goes like that. Both arms go upwards. Okay. 2, how could it have 2? Well, again, many ways we could probably come up with it. Let's try drawing a downward one. 1 x-intercept, 2 x-intercepts, and then it moves on. Okay, or maybe 1, 2, and then this other kind of change in direction happens there. Okay, it could even have 3, right? It could have 3, maybe 1, 2, 3, right? Like that. 1, 2, 3. Lots of different possibilities. Notice that really what this is about, these x-intercepts and the number it can have, we can kind of boil it down to how many times our function sort of changes direction, right? Since a cubic function changes direction twice, it can cross the x-axis, change direction and cross again, and then change for up to 3 x-intercepts. A quartic function changes direction up to 3 times, right? Not always going to do it 3 times, but up to 3 times. So crosses once, changes direction twice, changes direction 3 times, changes direction a 4th x-intercept. And again, if we imagine factoring a quartic function, right, we could have something like x plus some number, another number, another number, and another number, right? That gives us up to 4 possible ways to get 0, right? This would be a quartic function factored, okay? And so there's 4 different unique ways to make it equal 0. Now again, not always, right? It's possible that 2 of them are the same x-intercept, and that would only give us 3 unique, right? If that were if that factor showed up twice, that's only 3 unique x-intercepts. So it's key to remember it could have 4. That doesn't guarantee it will always have 4, but a quartic function can have up to 4, 0, 1, 2, 3, or 4. Quintic, very similar to the cubic, except we're adding in 2 more turns now, right? The function kind of changes directions 2 more times. And again, a quintic function, degree 5, the arms go in opposite directions, so it's guaranteed to have at least 1. It can't have 0, okay? But from there, it could only have 1. It might look something like this. Whoops, that's not going to work, is it? Wasn't thinking there. Could go something like this. Oh boy, I lost count. Think like that, right? Something like that could look, could have 2 x-intercepts. Maybe that's something like 1, 2. Then it goes like that, right? Could have 3, could have 4, could have 5, like we see here. Okay, I won't draw out every possibility, but you can imagine the different ways that it could change directions and cross the x-axis. Again, if we imagine factoring a quintic, we can see that it could have up to 5 unique factors, right? Again, if we just had f of x equals x to the power of 5, that's not going to have, it is a quintic function, but it's actually only going to have 1 x-intercept. Y is only 0 for that when x equals 0. Right? The graph of that looks something like this. Basically crosses it when x is 0 and then never again. Okay? So important to remember, degree 5 means it could have up to 5 x-intercepts. Doesn't necessarily mean it has 5. It could have 1, 2, 3, 4, or 5. Okay? All that means is it's possible the most unique factors this could have would be 5, right? If it had any more, it wouldn't be a quintic function. Okay, if there was another factor here, we wouldn't have an x times x times x times x times x, an x to the power of 5, right? We would have x to the power of 6. It would no longer be a quintic function. Okay, and again, this does kind of have, it has 5 factors. They're just not unique. It's x times x times x times x times x, right? This would be a quintic. x plus a to the power of 5. That is a quintic function, but it still only has one x-intercept. It's at x equals negative a, because negative a plus a would be 0, giving us a 1 x-intercept, one way to make y equal 0, one value of x that makes y 0. Okay, so key takeaway here, one of the key characteristics of a polynomial function is that the maximum possible number of x-intercepts is just going to be the degree of the quadratic. Oh boy, I got to change that. That's not the word I want there. Polynomial. They're not all quadratics, of course. Whoopsies. I'll fix that in the notes. Polynomial. We're going beyond quadratics. Okay, right? So degree 5 would have up to 5 x-intercepts. Degree 11 would have up to 11 x-intercepts. Okay? All right, we're going to take a look at some more of this stuff that will help hopefully now, understand why the cubic one arm goes up, one arm goes down, same for the quintic. But then for quartics and quadratics, both arms do the same thing. Let's jump into that here. All right, so the degree we know can tell us about the maximum possible number of x-intercepts. But it can actually tell us something else, and we were kind of getting into it a little bit there, but let's really think about this now, okay? So the shape of the graph is going to tell us about the equation's degree and leading coefficient, okay? And vice versa. The equation can tell us about the shape of the graph if we know how to connect the degree and the leading coefficient to the behavior of the graph. This is what we call end behavior. You'll see why, because it's about what the graph is doing at its ends. Okay, it's two ending arms as x goes off to negative infinity or positive infinity. Okay, so for degree, we can tell about the degree of a polynomial function by looking at the directions of both arms, comparing the directions of the two arms. For any polynomial with an even degree, so that's degree of 2, of 4, of 6, of 8, okay? Its two arms will end in the same direction, meaning that as x goes off to negative infinity or positive infinity, y is going in the same direction for both of those, right? So for this quadratic here, as x goes to negative infinity, it looks like y is going up to positive infinity. Same thing here. As x goes to positive infinity, y is also going up to positive infinity. Notice the two arms are doing the same thing. Here is the graph of this, 9x to the power of 4, even degree, degree of 4. Right arm goes up, left arm goes up. As x goes to positive infinity, y goes to positive infinity. Same thing as x goes to negative infinity, y goes to positive infinity. Here's one, negative 2x to the power of 6 minus 3x to the power of 4, blah, blah, blah. So degree of 6. Now notice, not necessarily, I didn't say they would both go up. I said they would both do the same thing for an even degree, right? So left arm is going down as x goes to negative infinity, y goes down to to negative infinity. And then same thing, as x goes to positive infinity, y is also going down to negative infinity. So left arm and right arm do the same thing. They both go down or they both go up for an even degree polynomial. Okay, now why? Well, that just seems like a magic trick, right? Why does that make sense? Because it actually does make a ton of sense. Raising any number to an even power is always going to give the same sign for our y output, right? Let's just use squaring because that's an easy one. If I square 1, I get 1. If I square negative 1, I get 1. If I square 3, I get 9. If I square negative 3, I also get positive 9, right? Notice, negative inputs and positive inputs give the same sign output, right? For an even degree, even power, okay? So as x goes off to positive infinity or negative infinity, if we have an even exponent there, we're always going to end up with the same sign output, okay? This works, obviously I just showed squaring, but it would work the same for to the power of 4, right? 1 to the power of 4 is 1. Negative 1 to the power of 4 is also positive 1, right? 2 to the power of 4 is 16. Negative 2 to the power of 4 is also positive 16. So as x goes to negative infinity or to positive infinity, if the degree is even, we still end up with the same sign on our y, right? And that's why both arms go up or both arms go down. Now you might be saying, hang on a sec, this was always positive. How do both arms go down then? How is that ever possible? Well, that has to do with, notice here, x was being raised to the power of 6, but then it's being multiplied by a negative 2, right? So just for another example, if I had negative 1 squared, well, 1 squared is 1, and make that negative, we get negative 1, right? What about negative 1 squared? Well, negative 1 squared is positive 1, right? And negative positive 1 is negative 1, right? Negative 2 squared is negative 4, because 2 squared is 4, make it negative, right? Negative 2 squared. Well, negative 2 squared is positive 4, make it negative, you get a negative 4. Okay, so see, this one, the difference between this one and those ones was that the leading coefficient here is negative. So when we take our x's and put them to the 6th power, since that's an even power, we're always going to get a positive number, but then when we multiply it by a negative, we get a negative number, right? So as x goes off to positive infinity or negative infinity, in either direction, we're just getting bigger and bigger negative numbers. And now you might be saying, well, yeah, sure, I can see why this term would always be positive or why this term would always be negative, but what about all these other terms, right? Couldn't they have any combination? And that's true, you're right. These could be like maybe, if as x goes to negative infinity, this is getting more and more negative, right? As x goes to positive infinity, this is getting more and more negative. This is getting more and more positive. So how do we know that overall y is going to get more and more positive or more and more negative as x goes to positive infinity or negative infinity? It seems like we're only caring about the degree. And that's a good point, but that's the key. The highest power on x is going to dominate the behavior of the function, right? As x gets larger and larger, as x goes off to positive infinity or negative infinity, what's going to be the biggest part of this equation, for example? Well, this by far is going to be the largest, right? Once x starts getting bigger and bigger, this really takes over, right? Like think about x being a billion, right? This is then a billion times larger than this because it has another multiplication of that x. So when x is a billion, this has now become a billion times larger than this, and a billion times larger than this, and a billion times larger than this, right? That's how many more multiplications of x are involved with that. So our end behavior, what we're looking at is the arms, right? The right arm and the left arm. That's talking about as x gets larger and larger to the right or to the left, right? And so these largest exponents on x, the ones that determine the degree, are the ones that overall kind of dominate the behavior of the function. And that's why when we look at what the right arm and what the left arm are doing, we can figure out if they did the same thing, we must have an even power as our highest exponent on x, okay? Now it's the same logic, but the kind of opposite result when we think about it having an odd degree, when the highest power on x is an odd number. Because for any odd exponent, okay, well, first let's just say what will happen. An odd degree polynomial function will have arms that end in the opposite direction, right? So again, not necessarily saying which one will go up and which one will go down, but that one will go up and one will go down, right? X to the 5th, we've got left arm goes up, right arm goes down. X to the 3rd, right arm goes up, left arm goes down. Just x, right arm goes up, left arm goes down, okay? But why? Why when we have an odd degree do the arms do opposite things? Well, again, it has to do with what we were talking about, right? As x goes to infinity, that's thinking about the right arm as x goes this way to positive infinity, right? Versus x going to negative infinity, right? The output will have opposite signs, for odd exponent? Don't believe me? Let's check, right? For example, let's just use cubed, because that's probably the easiest one to think about. If I cube positive 1, I get positive 1, because 1 times 1 is 1, times 1 is 1, right? But what if I cube negative 1? Well, negative 1 times negative 1 is positive 1, but then positive 1 times another negative 1, right, cubed, gets me back to negative 1. If I take a negative number and raise it to an odd power, I get a negative answer. If I take a positive number and raise it to an odd power, I get a positive answer, right? 2 to the power of 5. That's 2 times 2 times 2 times 2 times 2. It's 32. What about negative 2 to the power of 5, right? That's negative 2 times negative 2, which is positive 4, times negative 2, which is negative 8, times negative 2, which is positive 16, times negative 2 a fifth time, that's negative 32, right? So odd exponents give us opposite signs for when we put in a positive x versus a negative x. Unlike our even exponents, where we get the same sign out, right? Put in a positive and square it, you get a positive. Put in a negative and square it, you get a positive, okay? And so that's why for our odd degree polynomials, as we imagine x becoming larger and larger positive numbers versus larger and larger negative numbers, we're expecting y to do opposite things, right? A bigger and bigger positive might just give us a bigger and bigger positive y. A bigger and bigger negative might give us a bigger and bigger negative y. Okay, now again, that depends. It's not always the case that the right arm is going to go up, right? As x gets more positive, it gets more positive, because it is possible that we have a negative leading coefficient here. And so now as x becomes a larger and larger positive number, x to the fifth is positive, but we're multiplying that by negative 5 to get actually a really big negative number. And same logic here. Why do we only have to worry about the degree? Why doesn't it matter that there's also an x to the fourth here? Because the largest exponent is going to dominate the behavior of the function, right? X to the fifth is way, way, way bigger than x to the fourth as soon as we start getting into even x's that aren't that big, right? Like even when x is just 10, this is still 10 times bigger than this term then, right? I mean, ignoring the 5 and the 4, but roughly 10 times larger, right? Forget about it once we get up into like x being 100 or 1,000 or a billion, right? When x is a billion, this term is a billion times greater in value than this term, because this is a billion to the power of 5, this is only a billion to the power of 4, okay? And so that is why that fact that for odd exponents, positive numbers that we input give us the opposite sign as negative numbers when we input them, right? So raising a negative or a positive number to an odd power will always give opposite signs on the y outputs. And so the highest power then dominates the behavior of the function. Okay, so quick recap. What do we expect the arms to do for an even degree polynomial? Well, they're both going to do the same thing. That might mean they both go up, it might mean they both go down, but they'll both be doing the same thing. For odd, one is going to go up, one is going to go down. Okay? Now, if we put that together with the next thing we're going to talk about here, the leading coefficient, we'll be able to pick out quite a bit of information about a polynomial function just from its graph, or vice versa, about the equation, about the graph from just its equation. Let's try that. Okay, so for the leading coefficient, what we can do is look at the direction of the right arm. And if the right arm goes up, we know that the polynomial has a positive leading coefficient. Okay, so if the right arm goes up to positive infinity, that means that the leading coefficient was positive. Why does that make sense? Again, we've kind of been talking about these ideas, right? When we talk about the right arm, we're really thinking about what happens as x gets larger and larger in the positive direction, right? Well, the leading coefficient is attached to the highest power of x, right? And so if as x is getting more and more and more positive, y is getting more and more positive, right? Remember, this is the biggest thing. So if this is positive, right, if the leading term is positive, the leading term is the largest term because it has the highest power of x. So if we're getting a bigger and bigger positive number, as x becomes a bigger and bigger positive number, that just tells us that our leading coefficient must also be positive, right? We know x to the fourth is bigger than x to the third, and so if as x becomes larger and larger and larger, y is also getting larger and larger in the positive direction, we know we're not multiplying it by some negative coefficient, right? We're keeping it positive, multiplying it by some positive leading coefficient. This is still true for odd degree, right? Again, as x becomes a larger positive number, if y is just going up, becoming a bigger and bigger positive number, this must not have a negative attached to it, right? If there was a -1 here, that would mean that as x became a bigger and bigger positive, this would be getting to be y would be getting to be a bigger and bigger negative, right? But we know that's not happening, so we know the leading coefficient must be positive, right? The leading coefficient is attached to the highest power of x. As x increases, as x goes off to positive infinity, okay, that leading term is always the largest. So if it's positive, if that leading coefficient is positive, those positive y outputs kind of dominate. Again, it's totally possible that, maybe this term was negative. It wouldn't be in this case, but this will be larger. And so overall, y gets larger. So in other words, as x goes to positive infinity, okay, the largest term, which is the term attached to the largest power of x, is going to be greater than 0 if the leading coefficient is greater than 0, right? That's essentially what decides the sign of the leading term, right? Because x is going off to positive infinity if we're focused in on the right arm. So if the right arm goes upwards, we know that our leading coefficient is positive. All right, what if the right arm goes downwards? You can probably guess that a polynomial with a negative leading coefficient will have a right arm that goes downwards. Same exact logic, except flipped around, because now if our right arm goes downwards, that means as x is approaching positive infinity, as x is getting larger and larger in the positive direction, y is becoming a bigger and bigger negative number. Y is becoming more and more negative, right? Again, if I make x positive 1, this is negative 3. If I make x positive 10, this becomes negative 30. If I make x positive 100, this becomes negative 300. See what's happening? It's just getting further and further down on the y-axis, okay? Same logic here, right? X to the power of 6, as x becomes a larger and larger positive number, x to the power of 6 is getting to be a bigger and bigger positive number, but we're multiplying that big positive number by -2, making it a very large negative number, right? As this goes on, as x gets larger and larger in the positive direction, this just gets to be a bigger and bigger and bigger negative number, okay? Here, -5x to the 5th, as x gets larger and larger in the positive direction, sure, x to the 5th might be positive, bigger and bigger positive number for x to the 5th, but we're multiplying that x to the 5th by -5, making it actually a very big negative number. So, same exact logic, okay, but now if it's attached to a negative leading coefficient, as x increases, that leading term is the largest. So if it's a negative term, that will dominate the overall behavior of the function, right? So as x goes to positive infinity, the largest term, which dominates the behavior once x gets larger and larger, okay, is negative if the leading coefficient is negative. Okay, now the direction of the left arm doesn't tell us definitively about the sign of the leading coefficient, because as x goes to negative infinity, y's behavior will depend on both the degree and the leading coefficient. So we can't be quite as sure, right? Like you can't say, oh, the left arm goes to positive infinity, so this must have a positive leading coefficient. Well, no, right? Because this arm is going upwards because of the fact that we have an odd degree. And these negative x inputs are actually causing this to be negative and then multiplied by a negative to make it positive, right? So those are the two things we look for. What is the right arm doing? And are the two arms doing the same thing or opposite things? Okay, the right arm tells us about the sign of the leading coefficient. If right arm goes up, positive leading coefficient. If it goes down, negative leading coefficient. And then how the two arms act compared to each other, right? If both arms go up, even degree. Or if both arms go down, even degree. If one arm goes up and the other goes down, odd degree, right? And not just magical rules to be memorized or anything, okay? They make sense when we think about what's going on with that. Oh yeah, odd degrees, odd exponents give us opposite signed outputs when x goes to positive infinity versus negative infinity, right? Whereas an even degree, even exponents, will give us the same sign outputs, whether x is going to positive infinity or negative infinity, right? And then for leading coefficient, if the biggest term is attached to a negative, well then as that x gets larger and larger in the positive direction, we get a bigger and bigger negative. So right arm would go down, right? If it's attached to a positive coefficient, like these, right, then as x gets larger and larger in the positive direction, it just gets positive, bigger and bigger in the positive direction as well, right? So right arm goes up, positive. Right arm goes down, negative leading coefficient. All right, let's try this out. Let's see if we can practice it. All right, so let's try applying this here, okay? They want us to sketch these different combinations. So a positive leading coefficient, an even degree, and then negative, even, positive, odd, negative, odd, okay? Let's just break this down. Positive leading coefficient, do you remember? What does that tell us? What do we know about the behavior of the graph, the end behavior of the graph? Right, it tells us that the right arm goes up, okay? Now, all we're saying when we say that, right? I mean, that is not really the proper terminology here. The right arm goes up. What it means is that as x goes to positive infinity, y also goes to positive infinity, right? Which makes sense. If we have a positive leading coefficient, then our biggest term is just going to get more and more positive as x gets more and more positive. As we go right on the x-axis, we should just keep going up on the y-axis towards positive infinity. Now, even degree, do you remember what that tells us about the end behavior? Right, even degree means that both arms go same direction. Okay, and again, what does that really mean? Both arms go same direction? All that means is y approaches same value, right? Whether it's positive or negative infinity, when x goes to infinity as when x goes to negative infinity. Again, for those reasons we talked about, right? If you raise a positive number to an even power or a negative number to an even power, you're going to get the same sign result, right? Negative 1 squared is going to give us the same thing as positive 1 squared. Okay, negative a billion squared is going to give us the same thing as positive a billion squared. So let's put those two ideas together. We know the right arm goes up, and we know it has an even degree. So what could that look like? Okay, we know the right arm goes up, and we know that both arms go in the same direction. So if the right arm goes up, both arms go in the same direction, what does the left arm do? It must go up, right? That's kind of the way we can attack these, right? Figure out what the right arm's doing, and then figure out if the left arm's doing the same or the opposite, right? Or sometimes vice versa. So if the right arm is going up and the left arm is also going up, I mean, there's a million we could draw here. Could look something like that, right? Could look, could be a quartic. Apologies, I'm sure you can hear that siren in the background. Okay, could look something like this. Right arm goes up as x goes up to positive infinity, so does y, right? I mean, lots of different examples we could draw, but both arms need to do the same thing. Now here's an interesting question. Does this have a maximum value, a minimum value, or neither? Well, if we take a look, right, remember maximum means that's the highest, the greatest value of the function that's ever reached, and it never goes above that. So the graph hits a highest point and never goes above it. Minimum, same thing, but lowest. So it hits a lowest y value. The function has a minimum value that it never goes below. It gets that low, but never any lower. Or neither. It doesn't have a maximum or a minimum. Well, looking at our graphs here, right? For any even degree, we know that both arms do the same thing. So that tells us there will be a max or a min. Okay, it's going to have a max or a min. And then if we combine that with the fact that, all right, it has even degree, so both arms do the same thing, meaning that it will have a value it never goes above or a value that it never goes below. Combine that with the fact that we know both arms go up now, we can figure out that this must have a minimum, right? There's a minimum for both of these. There's a minimum right there, right? That's the minimum y value. Or this one has a minimum right there, okay? All right. Let's try this combination out. What about something that has a negative leading coefficient and an even degree? We've already established even degree tells us that both arms go in the same direction. What does a negative leading coefficient tell us? That's right. Tells us that the right arm goes down, right? And again, that just means as x goes to positive infinity, y is going to go to negative infinity. Because our leading term, the biggest term, as x gets larger and larger, is going to be negative, right? The leading term is negative, so as we make x bigger and bigger, we just get a bigger and bigger negative leading term, making overall the function become bigger and bigger in the negative direction. All right. So let's draw that out. What could that look like? We know the right arm goes down. We know the left arm does the same thing, so the left arm also goes down. Again, we could come up with infinite graphs that fit this description. You know, maybe one like that. Okay, or just a good old parabola that opens downwards. Something like that. Now again, it's asking us, does it have a max, a min, or neither? Well, again, for a even degree polynomial function, we kind of know that it will have a max or a min, right? Because both arms do the same thing. So somewhere in between this arm going down forever and this arm going down forever, there is going to be a point where it never goes higher then, right? If it has to finish over here going down and finish over here going down forever, somewhere in between it got to the highest it would ever be, right? So what is that, a max or a min? That is a max, right? We can see here this one has a max value, whatever that y is, right? This one has a max value, whatever that is. So even degree polynomial functions will have a max or a min. And then whether that's a max or a min is just going to depend on whether it opens upwards, right, with a positive leading coefficient, or opens downwards with a negative leading coefficient. Okay, new combination, odd degree positive leading coefficient. Well, once again, we know that positive leading coefficient tells us the right arm goes up. What does the odd degree tell us? It tells us that arms go in opposite directions, right? Again, not a magical fact, right? Not a magical fact. It actually makes a ton of sense when we think about it, because for an odd exponent, when we raise a positive x versus a negative x to an odd exponent, we'll get opposite signs out of those two things, right? So y approaches opposite values when x approaches positive infinity versus when x approaches negative infinity. Okay? All right. So if it's got a positive leading coefficient, the right arm goes up. But it has an odd degree. So what does the left arm do? Good. The left arm goes down. Okay? So if we draw, how about a linear? How about a good old linear function? We know them. We love them. Okay? There's a linear function. Right arm goes up. Left arm goes down. Okay? How about a cubic? A cubic. Maybe something like this, a nice cubic function. Ooh, that's a little wonky, but you get the idea, right? Left arm goes down, right arm goes up. Right arm goes up because of positive leading coefficient. Left arm does the opposite because of odd degree. Now, for these odd degree functions, okay, are they going to have a maximum, a minimum, or neither? Do they have a highest value that they never go above, a lowest value that they never go below? Or do they not really have a highest value or a lowest value? Yeah, they have neither, right? Look, this is going up forever. It's never stopping going up, right? This is going down forever. It's never stopping going down. So there is no value that it's ever going to hit and then not go lower than. It's always going lower as x goes to negative infinity. It's always going higher as x goes to positive infinity, right? And so this doesn't have, odd degree functions don't have a max or a min. So this references back to what I was saying earlier about how odd degree functions can't have zero x-intercepts, right? Because the two arms do opposite things, one's always going up, one's going down, right? Might be flipped, but one's going up, one's going down. They're going to have to cross the x-axis at least once, right? They're always going to have to cross the x-axis at least once. So that's what I was referring to back up here, where you notice, right? How come a degree 2 can have 0, 1, or 2 x-intercepts, while a degree 3, 0 is not an option, right? Well, that's why. For a even degree, both arms do the same thing. So it's totally possible to have it where it never crosses the x-axis, right? Which is not the case for a cubic or anything with an odd degree. Both arms are doing the opposite thing, so one of those will eventually cross the x-axis at least once. All right, let's finish up here. We know that odd degree means the two arms will do opposite things. And we know that a negative leading coefficient means the right arm will go down. So what's that going to mean? Right arm goes down. What's the left arm doing? Going up. Right. So maybe a linear like that, or, a cubic like this. Something like that. Right? Or even a quintic where there's another term thrown in there potentially. Okay? So again, though, this has neither a max nor a min. So there's basically the four combinations we can make, right? We could have positive with even, positive with odd, negative with even, negative with odd. And it all just comes down to thinking about, okay, what's the right arm going to be doing? That's what the leading coefficient tells us. And then what's the left arm going to be doing? Well, it depends. Is it doing the same thing as the right arm, even degree, or the opposite thing as the right arm, odd degree? And with those two ideas, we can work out the end behavior for the graph, or if we know the end behavior for the graph, we can work out the degree and the sign of the leading coefficient, which is pretty cool to be able to tell just by looking at the graph or just by looking at the equation. Okay, let's try putting together some of these skills now and see if from the function we can come up with a sketch of the possible shape and pick out some of the key characteristics, okay? So let's start with this one. Y equals 4x squared minus 3x. First thing it asks us is the degree. So what is our degree? Well, highest exponent on x is 2. So our degree is 2. So is that even or odd? Even. Leading coefficient, say LC for short, is the leading coefficient. Well, what is the leading coefficient? It's 4. That is positive, right? Positive 4. Y-intercept. Two ways we could look at this, right? Y-intercept is just the constant term. We can also just imagine putting in 0 for x. What would we get? Well, 0 minus 0. So our y-intercept is 0, right? Again, you could say, what is y when x is 0? If you really wanted to, show it here, well, it's 0, right? 4 times 0 minus 3 times 0 is still 0. Okay, so we now know that the y-intercept happens at 0. We know that it has an even degree, and we know that it is a positive leading coefficient. The next thing it asks us is the possible number of x-intercepts. Okay, so this has a degree of 2. So even, so it's possible for it to have 0. It's possible for it to have 1. It's possible for it to have 2. Is it possible for it to have 3 x-intercepts? No, right. If it had 3 x-intercepts, it would have to change direction twice, which we know a quadratic doesn't do, right? Or it would need to be able to be factored into 3 unique factors of x. Well, it can't. We know a quadratic at most could have 2 unique factors, okay? So 0, 1, or 2. So a sketch of a possible shape, obviously this might not be perfect, but let's just work through what we know. Even degree and a positive leading coefficient, and then a y-intercept at 0. So we've got a y-intercept at 0. I'm going to draw the y-intercept in first. Now, what do we know about the right arm if it has a leading coefficient? We know that the right arm goes up. Okay, so we know the right arm goes up. And what do we know about the left arm if it has an even degree? We know it also goes up. Right. And it could have 0, 1, or 2 x-intercepts. So again, we could go into some of the quadratic stuff, but they just want a rough sketch. I happen to know that this one looks something like this. Okay. All of that information just based on looking at the equation. Okay. We've met all the possible criteria here. It has 2 x-intercepts. Okay. It's got a right arm that goes up, and the left arm does the same thing. All right, let's try this one out here. Ooh, they're trying to trick us. What's the degree of this? Careful, it's not 1, right? Remember, nobody ever promised that they would always give it to you in standard form. So our degree is 3. That is the highest exponent on x, right? 2x cubed. Okay, leading coefficient. Once again, be careful, right? Not in standard form, but that doesn't change the fact that the standard form is the coefficient for the highest exponent on x. So our leading coefficient is -2. All right, degree is 3, so that means our degree is odd. Leading coefficient is -2, so obviously that's negative. And what would be our y-intercept here? Well, we can look at the constant term, right? What's our constant term? -1. Again, you can always imagine putting in 0 for x, right? 0 minus 1 minus 0 is -1. So it's going to be at 0, -1. Okay. Possible number of x-intercepts. It is a cubic. It's a cubic. So keep in mind what we already know. We know the 2 arms do opposite things. One goes up, one goes down. Can it then have 0 x-intercepts? No, it can't, right? If one arm's going up forever, one's going down forever, it has to cross the x-axis at least once. So it could have 1 x-intercept, or 2, or 3, but it can't actually have 0. Okay? All right. So let's do a decent sketch of this then. We know the y-intercept is at 0, -1. Okay, so something like that. What do we know about the right arm? Well, it's got a negative leading coefficient. So our right arm goes downwards. Right? Our right arm goes downwards. And what does the left arm do? The left arm goes upwards. So it might look something like that. Right? Again, it might actually have, it could look something more like this. Whoops, nope, not like that. Right, it's possible that it changes direction one more time than that, but that's a rough approximation. Okay, that meets all the criteria that we can tell just by looking at the equation. Okay. Last one here, trying it out. 8 plus x minus 2x squared. They're trying to trick us again, right? They're trying to trick us again. They didn't write it in standard form, so don't fall for that. We know that the degree is just the highest exponent on x. No promise that it will always be in the leading spot. That's standard form. That's the polite way to write it, but no guarantee that they are always going to be polite. So if the degree is 2, that is an even degree, and our leading coefficient is -2. So it's got a negative leading coefficient. Okay, y-intercept here. Well, we can look at the constant term and see that it's 8. Again, we can also imagine putting in 0 for x. 8 plus 0 minus 0 is 8. So our y-intercept happens at 0, 8. Okay, possible number of x-intercepts. This is a quadratic. It is possible, since both arms go in the same direction, it is possible for it to have 0 x-intercepts, but it could also have 1, it could also have 2, right? We'll have to factor them to really start thinking about their x-intercepts, or you can always graph them quickly on your graphing calculator to see, okay? But again, we can actually, kind of figure this out. how many it will have because we know that the right arm goes down and we know that it has a y-intercept up at 0, 8, right? So we can actually figure out that in this case it will have 2 x-intercepts, right? We can figure that out because how is it supposed to be up here and have both arms going downwards and not cross the x-axis in 2 different places, right? It really can't. It's going to look something like that. I think it actually ends up, if you really graph this one, it ends up looking more like that. Okay, but there we go, right? We can figure out, well, if it's up here and both arms go downwards, it's going to have to cross the x-axis twice, right? We knew it could have 0, 1, or 2. Now we can kind of conclude that, oh yeah, this would have to have 2 x-intercepts. But there's a rough sketch based on the information we were given. Even degree, so both arms do the same thing. Negative leading coefficient, so right arm goes down. And again, that means the left arm goes down since we know they do the same thing. Constant term told us the y-intercept. And we knew it had 0, 1, or 2. With a little bit of thinking about it, we can figure out it needs to be 2. All right, so go ahead and give this one a shot here. Just getting you to think about using the degree and the sign of the leading coefficient for each function to describe the end behavior. That's saying, what is the right arm doing? What is the left arm doing? As x goes to positive infinity or negative infinity for the corresponding graph. It also wants us to state the possible number of x-intercepts and the value of the y-intercept. Go ahead and try that one out, and you can try some of the other practice questions around that while it's fresh in your brain. Take a little practice break, and then we'll move on, kind of change speed here to talk about dividing polynomials. All right, so we've been talking about graphs of polynomials and what we can tell based on the degree and the leading coefficient and all that. We're going to do something here that's kind of going to feel like a shift in our focus, okay? But it actually is connected. What it's building up to is being able to factor these polynomials. And being able to factor them will allow us to determine its x-intercepts or its solutions if it's part of a polynomial equation, okay? But in order to do that, we need to remind ourselves of long division, because that's what we're actually going to do with polynomials. We're going to divide them using long division. Now, it's been a while, I get it, for long division. You divide stuff all the time, and you do it so much that it's possible you've maybe like kind of forgotten about what it's really about, right? What is division really about? It's actually a way to determine how many times one number can be put into another number. Right? I know we've been doing division for so long now that we kind of forget that fundamental definition of it, right? Why is 8 divided by 2 4? We kind of just say it, 8 divided by 2 is 4. But don't forget, back when you first learned about division, right? It's because 4 2's fit into 8, right? Count them out. 2, 4, 6, 8. If you count it along on your fingers, you'll see that 4 2's fit into 8. That's what we're saying. How many 2's can go into 8, right? It's essentially a way of saying, how can we take 8 and split it up into 2 even groups is another way to look at it, right? 8 divided into 2 groups would give us groups of 4, okay? So the dividend, the divisor, and the quotient, and the remainder, those are some terms you might not have heard in a while, okay? But they're parts of a division that we're going to be referring to as we go here. So the dividend, that's what we call the number being divided. So for our example of 8 divided by 2, 8 would be the dividend. We're dividing 8 by 2. The divisor is the number that the dividend is being divided by. So 2 in that example, right? 8 divided by 2. The quotient is the answer, so to speak. It's how many times the dividend fits into the divisor, right? 4 in that example would be our quotient, since 8 divided by 2 equals 4. And then we have something called the remainder that you haven't talked about much in a while, right? But the remainder is kind of what's left over. It's the part of the divisor that cannot fit into another group of the dividend, right? Or that we cannot fit into. It's how much of the divisor cannot fit into the dividend, right? So in this example, in this 8 divided by 2 equals 4 example, 0 is actually our remainder because 8 can be perfectly divided by 2 into 4 groups of 2, right? We can take 8 and split it up into 4 different groups of 2, okay? So our remainder is 0. Nothing left over. 2, 4, 6, 8. For an example where the remainder is not 0, how about 11 divided by 4? So how many times can 4 go into 11? Well, twice, right? Because 4, 8. But can it go in a third time? Not into 11, right? 4, 8. A third 4 would give us 12. So 4 goes into 11 twice, 4, 8, and then we've got 3 left over. We can put 3 more into 11, but we can't put a full other group of 4 into 11, right? So it goes into 11 twice with 3 remaining, okay? 2 4s equals 8, and another 4 cannot fit into 11 because 3 4s would make 12. So we have a remainder of 3, we would say, right? 11 minus 8. Okay, there's 3 left over to get to the 11. So what we would say is 11 divided by 4 is 2 with a remainder of 3. This remainder of 3, what that's saying is that altogether we can fit 2 4s into 11, and we can't fit another full 4, but we can fit 3/4 of a 4, right? We can only fit 3 out of 4 4s into 11 after we've done 2, right? We can fit 2 full 4s and then 3/4 of another 4, right? So that's why your calculator tells you 2.75 when you enter 11 divided by 4. It's saying you can fit it in 2 3/4 times, 2 full 4s, and then 0.75 of another 4 can go into 11, okay? So in previous grades, you've showed this with long division. This is how we represent division when we first encounter it, okay? We're actually going to kind of go back to this for polynomial long division. That's why we're doing a little reminder on what division is in the first place here and what we're really saying, right? So just for an example here, right, 4 into 11, well, it goes twice. And then what we're doing in this step, we divide, multiply, subtract, bring down, divide, multiply, subtract, bring down. I don't know if you learned the algorithm that way, okay? But what we do is we say, well, how many times can 4 go into 11? Twice. And then we multiply, so 2 times 4 gives us 8. What we're essentially doing there is saying, okay, what is 2 4s, right? Well, 2 4s is 8. And then we subtract to see what's left over, right? So 2 4s gives us 8. Subtract the 8 from what we started with, 11, to get that we would have 3 left over, okay? We can put 4 into 11 twice. That would give us 8, meaning that we're left with 11 minus 8, which is 3. So we often represent this in the form of a division statement, okay? It's basically saying if you divide the dividend by the divisor, it can go in this many times with this much of the divisor still left over. So for 11 divided by 4, right, 11 divided by 4 is going to be 2. It can go in twice, okay, but we'll have a leftover of 3/4 of another 4, right? We can put 2 full 4s into 11, and we're left with 3/4 of another 4 that could go in still. Okay, we can't put we can't put 3 4s into 11, but we can put 2 in and then 3/4 of another one, right? So together what this is telling us is that 4 goes into 11 2 3/4 times, right? Or 2.75 times, which is exactly what you'll get if you do 11 over 4 on your calculator, okay? All right, let's try reminding ourselves of long division here before we go into polynomial long division, just because it helps to have a base, reminder of what long division looks like, how it works, the steps involved in the algorithm before we take it into polynomial territory. Okay, so it wants us to do 7 divided by 2. We're way back in our math classes now, early math where we first learned about division, okay? How do we represent this? We say 2 and 7, right? This is now our dividend, and this is our divisor, and we're asking ourselves, how many times does 2 go into 7, okay? So the steps are divide, multiply, subtract, bring down. I'll just put them there so we can reference them. And again, these aren't just random steps. It's talking about how many times does 2 go into 7. Multiply to figure out how much that represents, subtract to figure out what's left over, and then we bring down in case there's more parts of the number to continue dividing, okay? So divide, how many times does 2 go into 7? Well, 3 times, right? It definitely goes in 3 full times. 3 times 2, so I did the divide part. I put the quotient up here. I multiply now, so 3 times 2 is 6. And what we've just figured out is, okay, 2 goes into 7 3 times. That gives us 6. 3 2s is 6. Now we subtract to figure out what's left over, right? What do we still have left? 7 minus 6 is 1. And then we would bring down if there were something to bring down. But this is it. 7 really was our entire number. We weren't dividing it by like 70 or something like that, or 75, right? So this is just left over, which makes sense, right? How many times does 2 go into 7? Well, 3 times, but then you'll still have 1 out of 2 that you could put into it, right? You'll have half of a 2 that you could still put in. So we've got here, let me just look at the parts. We've got our remainder. That's what's left over. There's nothing left to do, so we're finished. We've got our quotient. This was our dividend, the thing that was getting divided. Dividend. And this is our divisor, the thing we were dividing it by. So if we look at our division statement, okay, what we tried to do, what we did was 7, dividend, over 2, divisor, 7 divided by 2, okay, and we found that it was equal to our quotient, so it went into it 3 times, but we're left over with 1 over 2, right? 1 over 2. So what this is saying is that you can fit 3.5 2s into 7, which is true, right? You can fit 3 2s into 7, but then you've still got half a 2, or 1, left over, okay? So 7 divided by 2, you probably know, is 3.5, right? 3.5, okay? Again, I know you probably know that, but we're just reminding ourselves of the process of long division, because we're not just going to be able to plug in polynomial long division into our calculator. So that's why we're reminding ourselves with some numerical examples of the algorithm involved with long division. Let's try this one. So now we're dividing 320 by 12, right? So let's set it up. Again, nice little trip down memory lane here. Been a while since we did this, right? Whoops, I didn't really give myself any room there to write in the quotient. 12 into 320. Okay, let's remind ourselves of how this works. Okay, so first things first, divide. Okay, now we can't put 12 into 3, so when that happens, we move on to the next thing, right? So we essentially say, okay, we can't put 12 into 3, but can we put 12 into 32? Yes, we can, right? We can do it twice. Okay, 12, 24, 36. So divide, multiply now to figure out what that represents, right? How 2 times 12 is 24, right? And the reason we're doing that is to be able to say, okay, so what's left? And again, we're going to subtract here. 32 minus 24 is 8. Divide, multiply, subtract, bring down. And the bringing down is just us recognizing that really this wasn't a 3, it was a 300, right? And this wasn't 32, it was part of a 320. This was in the 10 spot, this was in the 100th spot. So we're reminding ourselves that, okay, 12 can go into those 300s, right? 20 times. This actually represents a 20, okay? 12 goes into 320 20 times. Well, more than that, but that's what we're doing here, okay? So we're going to bring down the 0 to remind ourselves that we're actually dealing here now not with just 8 left over, but 80 left over. So now we ask ourselves, how many times can 12 go into 80? Well, 6 times, right? Because 6 times 12 would be 72. So 6 times 12 is 72. Divide, multiply. We just multiplied. Now we're going to subtract. 80 minus 72 is 8. And there is nothing left to bring down, so we are done. 8 is our remainder. So what's our division statement? Our division statement is that we tried to divide, well, we didn't try, we succeeded. We did 320 over 12, 320 divided by 12. We found that it goes into 320 26 full times. That's our quotient, 26 full times. And then we'll have 8 over 12 left, right? So we can't fit a full another 12 in, but we can fit 8/12 of it in. So plus 8 over 12. Okay, and we could reduce that fraction if we want, because those are both divisible by 4. 8 over 12 is really just 2/3, right? So 320 divided by 12 is 26 plus 2/3. And if you put it in your calculator, 320 divided by 12, you're going to get 26.66667, right? Means that 26 12s go into 320 with 2/3 of a 12 left over, okay? So we remind ourselves of that process there because we can actually divide polynomials by other polynomials using the exact same long division process that we just used, okay? So that's why we're reminding ourselves of that little algorithm there, okay? In Math 30-1, we're only going to divide polynomials by first-degree binomials. You could technically do it with larger polynomials, like you could divide by a trinomial, okay? But we're just going to do first-degree binomials in Math 30, okay? But it's going to look pretty similar, except instead of dividing numbers by numbers, we're going to be dividing polynomial expressions by other polynomial expressions. And again, why are we doing this? I know it seems a little bit random, because this is going to help us eventually in the next lesson factor polynomials, right? We know factoring and division are closely related, so that's where we're headed. So, long division of polynomials, how does it work? I'll run through the steps here. They're probably going to be, not the easiest to follow until you actually see it in action, but right at the top here, I want to give you a broad overview of what we do, okay? First things first, you need to make sure each is in standard form. So both the divisor and the dividend need to be in standard form. That's highest exponent of x down to the lowest exponent of x, okay? Then all we do is divide the first term of the dividend by the first term of the divisor. That's kind of the nice thing here. You're just going to use the first term of the divisor in each step, okay? And then whatever you get, that is part of your, answer, part of your quotient. It's the first term of the quotient. Our quotient will be a polynomial itself, so it will probably have more than one term, okay? But that will be our first term. Notice, very similar to what we were just doing, right? Divide and put whatever you get up as the quotient. Then, after divide, we multiply. So multiply the divisor by that first term of the quotient, the one you just got, and put the result below the dividend. Divide, multiply. Up next, we're going to subtract to create a new polynomial. And then bring down. So divide, multiply, subtract, bring down. Important note here, make sure you're lining up the terms so that you're subtracting like terms. The nice thing is you should always be able to check your work as you go because you'll always get 0 from the subtraction of the first two terms in this step. If you did it correctly, you're always going to end up, when you subtract the first two terms, you'll end up with a 0 here, and then you just kind of focus on what you're left with and repeat. So you're going to get a new polynomial after that subtraction, repeat, just like we were doing up here. Divide, multiply, subtract, bring down, right? Essentially, divide, multiply, subtract, bring down, and then repeat. Divide, multiply, subtract, bring down, okay? And just like before, you keep going until the new polynomial cannot be divided by the first term in the divisor. At that point, you're done. Whatever is left is your remainder, okay? And then you can always check your work, right? Remember, we're dividing here, so we should be able to undo the division by multiplying and get back to where we started, right? We can check our work by multiplying the quotient by the divisor and then add the remainder. And we should get the dividend that we started with, right? Same logic as dividing 11 by 4, right? We said that the answer was 2 remainder 3 because 2 4s will go into 11 with 3 left over. Sure enough, right? 4 times 2 is 8, and if we add the remaining 3, we get 11. So we can always check our work at the end the same way, Okay, so let's try this out here with a kind of a written out example for us where we can follow these steps in action. So let's say we wanted to divide this trinomial x squared plus 4x plus 5 by this binomial x plus 1. Okay, we'd write out x plus 1 and we're going to divide it into x squared plus 4x plus 5. Okay, so first things first, divide. Okay, so, well, and also check that they're in standard form, but these ones are, so we're good. All we're going to do, divide x squared by x. Okay, the first term of the dividend by the first term of the divisor. So x squared divided by x is just x, right? X squared over x equals x. X squared divided by x is x, right? You can think of that as x times x over x. So that's just going to give us x. Okay, x over x is 1. And there we go. We put it up as the first term of our quotient. Step 1, done. We divided first term by first term. X squared over x is x. Divide, done. Now we multiply. So now we're going to multiply that x by x plus 1 to start creating our new polynomial, the next step for us. Okay, so x times x plus 1. Well, x times x is x squared. X times 1 is just x. So now we have an x squared plus x here. Okay, so we divided, we multiplied. Now we're going to subtract. This is why I said make sure you line them up, right? Because when we subtract, we want to make sure we're subtracting like terms. Just makes it easier, right? You don't want your x squared over here, so you're thinking, oh boy, x squared minus x squared. Just line them up so it's easy to subtract straight down the line, okay? So now we're going to do x squared, right, minus x squared is 0. Remember what I said? We should always get 0 for that first term subtraction there. That's the nice thing here. I also recommend put brackets around this just so you can remember that you're subtracting all of this. Sometimes students just put the minus here and then they forget that they're actually supposed to be subtracting the x as well, and they do 4x plus x. I find the brackets helps me remember that both of these are being subtracted. So x squared minus x squared is 0. 4x minus x is 3x. So we've now divided, multiplied, subtracted, and we bring down the 5. So our new polynomial that we're just going to start from square one with and repeat, okay, is 3x plus 5. We just repeat these steps with 3x plus 5 as kind of the next thing we're dividing by, okay? So same thing. Take this, take the first term of our polynomial, divide it by the first term of the divisor. So we're going to do 3x divided by x, which is 3, right? 3x divided by x. X over x is just 1, so that equals 3. So that is the next term in our quotient. It goes up here as the next term in our quotient. So far we know that x squared plus 4x plus 5 divided by x plus 1. So far, it's giving us the polynomial x plus 3. So we divided, multiplied, subtract, brought down, and then we divide it again. Our next step would be multiply. Okay, so now we're going to multiply that 3 that we just got. Whoops, multiply that 3 that we just got by our divisor. 3 times x plus 1 is, well, 3x plus 3. Okay, time to subtract. So again, line them up. Nice little way to check our work as we go. 3x minus 3x is 0. That's good. We should always get 0 there for that first part of the subtraction if we did it correctly. And then 5 minus 3 is 2. So our new polynomial at this stage, after we divided, multiplied, subtracted, and brought down, is just 2. Now, 2 cannot be divided by x, right? 3x could, and so could x squared, but 2 can't, right? 2 over x does not really give us anything other than 2 divided by x. So 2 cannot be divided by x. There's nothing left to bring down, so we are done. 2 is our remainder. So as a division statement, dividend over divisor equals quotient plus remainder over divisor, we would write this as x squared plus 4x plus 5 over x plus 1 equals x plus 3. That's our quotient, right? X plus 3 plus 2 over x plus 1. right? We can fit x plus 3, x plus 1s into this with a leftover of 2 over x plus 1. I know it gets a little bit abstract because we're not dividing numbers here, we're dividing functions, so it can be a little bit weird to think about, okay? But we just divided a trinomial by a binomial, and this is the quotient and the remainder, and that's our division statement. How could we check our work? Well, the same way we could check that 11 divided by 4 is 2.75 by multiplying 4 by 2 and then adding 3 out of 4, right? Adding 3, okay? Same thing here. We can check our work by multiplying the quotient by the divisor and adding the remainder. Essentially what we're doing here, you can notice this by looking, we're saying if this over x plus 1 is equal to this stuff, if we multiply both sides by x plus 1, right? If we multiply this stuff by x plus 1, and it really is equal to this, then we should just end up with x squared plus 4x plus 5, right? Essentially what we're doing is that if this is really equal to that, then let me check by doing this, right? Because then this should just cancel out, and what I should be left with on this side should just be equivalent to x squared plus 4x plus 5. That's essentially what we're doing when we check our work here. Okay, so what I'm doing is I'm taking this side here, multiplying it by x plus 1 to see if it gets me back to where we started, x squared plus 4x plus 5. So if I multiply this side by x plus 1, I'll have x plus 3 times x plus 1 plus just 2 now, because that x plus 1 times 2 divided by x plus 1, the x plus 1s would just cancel, right? So now if we multiply this all out, x times x is x squared, x times 1 is x, 3 times x is 3x, 3 times 1 is 3, plus 2, collect like terms, x squared, x plus 3x is 4x, and 3 plus 2 is 5. Hey, sure enough, we get the original dividend that we started with, right? So it does seem like this stuff is equivalent to this, because when I multiplied this by x plus 1, I just got x squared plus 4x plus 5, right? Which is undoing that division by x plus 1. So we got the original dividend out. We know our answer is correct, okay? So just for convenience, we often, when we're doing this polynomial division, we often represent the dividend, divisor, quotient, and remainder in the following ways. Since the dividend is like the polynomial that we're starting with and trying to divide by something, we often just call it p of x. Just means it's a function of x, and p for polynomial, okay? The divisor we say is x minus a. That's going to come up especially when we start thinking about what our divisor can represent in terms of a potential 0, okay? But it's just a binomial, so we just say it's x minus a, where a is some number, right? A first degree binomial, okay? The quotient is also a polynomial. It's also a function of x. Since it's a quotient, we call it q of x. And the remainder, very creative, we give it the letter r. So you can sometimes see a division statement represented like this, right? Rather than writing out all of those long, the dividend over the divisor equals the quotient plus the remainder over the divisor, right? Obviously that gets a little bit annoying to write. So we sometimes just say p of x over some binomial can equal q of x, the quotient, plus the remainder over our divisor. How much of the divisor didn't fit, okay? Or in the kind of, I'll call it the check your work format, where we've multiplied both sides by x minus a. You can check that there, right? If I multiply this side by x minus a and this side by x minus a, our polynomial will be equal to the quotient times the divisor plus the remainder. Okay, again, that's just multiplying both sides by x minus a. Ready to try it out? Let's see if we can perform this polynomial division using long division. Alrighty, here we go. So we want to divide x squared plus 7x plus 17 by x plus 3 using long division. So here we go. My divisor is x plus 3. I want to divide that into x squared plus 7x plus 17. Okay, so we're just going to work through the steps. First things first, right? First things first would be to make sure they're in standard form, but they are, okay?
So divide, multiply, subtract, bring down, repeat, okay? So I'm going to take the first term, x squared, and divide it by the first term of my divisor, x. X squared divided by x is just x. There we go, divide. Now multiply, so x times x plus 3, well, that's going to be x squared plus 3x, right? X times x is x squared, x times plus 3 is plus 3x. So divide, multiply, subtract now. And again, I like to put brackets around it just to make sure I remember I'm subtracting that whole thing. Okay, so x squared minus x squared is 0. Hey, is that a good sign or a bad sign? That is a good sign. We should always get 0 for that first part there. And then 7x minus 3x is going to be 4x, positive 4x. Okay, positive 7x minus 3x is positive 4x. All right, we divided, we multiplied, we subtracted. Time to bring down. So I'm going to bring down this 17 plus 17. And now I just repeat, okay, with what I've got here. So 4x plus 17 is like the new polynomial that I'm now dividing by, okay? 4x divided by x is just 4, right? 4x divided by x just leaves me with 4. So I divide it again, time to multiply again. 4 times x plus 3, well, 4 times x is 4x. 4 times 3 is 12. So divided, multiplied, time to subtract. And I like the way this is looking because 4x minus 4x is 0. That's always a good sign. We should always get 0 there for that first part. 17 minus 12 is 5. And now, can we divide 5 by x? No, not really, right? So our remainder, oh, and there's nothing left to bring down. So our remainder is just 5. Okay, that's our remainder, 5. So as a division statement, we could say, okay, that p of x, our x squared plus 7x plus 17, divided by x plus 3 is equal to our quotient. Our quotient is x plus 4. I just like to put it in brackets just to make things a little more clear, plus the remainder over the divisor. Our remainder is 5, and our divisor was x plus 3. Okay, that is the result. Let's check our work. Okay, again, we're saying that when we divide this by x plus 3, it's apparently equal to this. Well, so if I undo that division by multiplying this by x plus 3, I should get x squared plus 7x plus 17, right? These sides cannot be equal if, when I multiply both sides by x plus 3, I don't end up with this side being equivalent to x squared plus 7x plus 17, right? So let's just see. We'll check our work if that's true. Does x squared plus 7x plus 17, does it equal x plus 4 plus 5 over x plus 3 times x plus 3, right? That's essentially what we're doing. So I'll put a question mark there because we're saying, does it equal? Well, let's just multiply that x plus 3 in. So I'm going to have x plus 4 times x plus 3 plus, and then when I multiply this by x plus 3, what am I going to be left with? 5 divided by x plus 3 times x plus 3? Well, I'm dividing by x plus 3 and then I'm multiplying by x plus 3. Those are just going to cancel each other out, right? X plus 3 over x plus 3 is just 1. So I'm just end up with 5. Okay, let's see. Doesn't quite look like x squared plus 7x plus 17 yet, but we haven't expanded this out yet. Let's see. X times x is x squared. X times 3 is 3x. 4 times x is 4x. And 4 times 3 is 12. And then we've got this plus 5 that was been along for the ride. And oh, look at this. 3x plus 4x is 7x. And 12 plus 5 is 17. So it worked. right? It does equal what we started with, the polynomial we started with, right? So we verified our answer now, okay? We said that when we divided x squared plus 7x plus 17 by x plus 3, it equaled this stuff. So if I take that quotient, that result, and I multiply it by x plus 3, I should just end up with x squared plus 7x plus 17. And sure enough, we did. So it works. We're feeling pretty confident in that answer now. Okay, so what I'm going to show you next is synthetic division of polynomials. Now, after I show you this, most students say, why didn't we just do this? Why did we bother with long division? Okay, because it's a way of taking long division and simplifying it down. And there's a couple reasons for that. The reason we still show you long division is that synthetic division really only works for binomials. Now you might be saying, but in Math 30 you said we'd only divide by binomials, so don't we only need synthetic division? Yes, but eventually in your math career you might need to do more, so we still want to have that foundation of long division. The other thing is that long division kind of checks out with what we're used to doing for division, right? Where we're following that usual algorithm and that process that we know from earlier grades. Synthetic division, if it's your first introduction to the idea of dividing polynomials, it can kind of seem like a magic trick. It's based on the same principles. It's essentially what people have done is taken what long division does and come up with a way to like optimize the algorithm, essentially to optimize it so that it works really well for specifically dividing by binomials. Okay, so it only really works for dividing by binomials. It will always work for us in Math 30 because that's all we have to do, but that's why we start with the long division. Okay, so you should be comfortable with long division, but I'll be honest, once you learn synthetic division, you will mostly just use that, mostly because it's faster and it's a little bit easier. Okay, it's harder to make a mistake. I don't think it's actually easier, but it's easier to keep track of and go through. Okay, so again, you could be asked about long division. The diploma might show you a long division process and say, where did the student make a mistake or something like that? So it's still good to get some practice with it and be comfortable with it. But synthetic division, I will admit, is a little more convenient. I don't know, maybe not. Some people prefer long division. Let's run through synthetic division and you can decide for yourself, okay? All it really is an alternate way of representing the division of polynomials, and it actually accomplishes the exact same task as long division, okay? It just takes things and simplifies them a little bit to kind of optimize the process. So we actually don't even write in the variables because ultimately what ends up mattering is what we're dividing in terms of like coefficients for like the numbers we get out, okay? Now the trade-off there is we do have to like represent stuff in a simplified way and understand what it means still at the end, whereas for long division, not so much. Like we still know obviously that this is a 4x and this is a 17. You can see for synthetic division, we're going to have to kind of apply that meaning back to it when we're done, okay? But we do a few things to simplify. We only use the coefficients of the dividend and we basically ignore the variables, okay? And we also only use the a part of x minus a for the dividend, okay? Now, where we are eventually headed with this, again, I know it seems kind of random. In the next lesson, we're going to start using these skills to factor polynomial functions, okay? Now, what we're doing when we're factoring, as we kind of alluded to earlier in the lesson, is actually looking for when we're factoring, we're kind of looking almost for x-intercepts, right? If I wanted to factor something to find its x-intercepts, I might take, you know, something like x squared plus 2x plus 1 and factor that to x plus 1 times x plus 1 to figure out that, oh, it has it actually has one x-intercept, but it shows up twice. It's -1, okay? X equals -1 makes that function 0. So what we're looking for, the reason we're so focused on this and this a value is we're eventually going to use this to test for x-intercepts and to find x-intercepts, and therefore to eventually find factors, which will allow us obviously to factor a polynomial function. So that is why we're like focused in part on that x minus a format, okay? And again, we're using synthetic division to eventually test for zeros, x-intercepts of the polynomial. And a is just what's going to make the divisor 0. A is the value of x that would make this 0, right? So if I had, you know, x x plus 1. The value of x that would make this 0 is x equaling negative 1, right? If I have x minus 2, the a value, the x that would make this 0, is if x equaled 2, right? 2 minus 2 would be 0, okay? So we're going to use just that a value for our division. It's simplifying things down here a bit in synthetic division. So we're actually going to do the exact same one here, just to convince you really that synthetic division is doing the same thing as long division, okay? We'll jump in again. It's kind of hard, I know, to make sense of this before you see it in action. So let's try it out. Suppose we wanted to use synthetic division to do x squared plus 4x plus 5 divided by x plus 1. Exact same one we just did with long division. If synthetic division really works, we should end up with the same result, okay? So first, make sure the dividend is in standard form, as that's the order we're going to write the coefficients in when setting up, okay? Luckily for us, this is already in standard form. If it weren't, we would have to rearrange or it's not going to work, okay? The algorithm here is it's set up to work when you have it in standard form, and something we'll talk about later, when every power of x is represented, okay? Not an issue here because we do have an x squared, then an x to the power of 0, okay? But it's already in standard form. What are our coefficients? 1, 4, and 5, okay? So for synthetic division, we're going to represent that as 1, 4, 5, just the coefficients, okay? Notice, for synthetic division, we leave some room underneath. We're going to need it later, okay? Now, what's our divisor? Our divisor is x plus 1. Again, because we're thinking of this as like a potential x-intercept, we're going to always think of that as like x minus a. So if x minus a is x plus 1, what is a? Well, that would mean, right, if x minus a is x plus 1, what's our a? Our a is negative 1, right? X minus negative 1 would be x plus 1. So our a here is actually, the a part of our divisor is actually negative 1. And where are we going to put that? We're going to put it off to the left here for synthetic division, okay? And from here on out, it's actually super fast, super quick, okay? I know this does seem a little bit magical, I won't lie, okay? It is a well-tested and developed algorithm that works really well. There's stuff going on behind the scenes that we could get into, but in the interest of time and what we have to cover in a short quarter, okay, you can do some extra research on your own. Where does the algorithm for synthetic division come from? Okay, it is based on all the same ideas we've been using for long division. It's basically just been made to be the most efficient form of it, okay, by taking advantage of some math stuff. So since a is negative 1, we would set it up like this. From here we go, okay? We always are going to do the same thing first. We're going to bring this number down. So I'm going to bring down that 1, put it there, okay? There we go. Step 1, done. Now what do? We multiply that by our a value that's sitting here to the left. So we're going to do negative 1 times 1, which is negative 1. And that negative 1 goes up here, okay? So we multiply the negative 1 by 1. That gives us negative 1. Put it up here. Now all we do is add down that column, and that gives us the second coefficient of our quotient. These eventually will tell us the coefficients of our quotient. So now we add 4 plus negative 1 is 3. And we're just going to keep going until we're done. We just repeat that process. So first, bring down, multiply, add, multiply. That's our next step here. So we're going to multiply negative 1 by that 3. Put the negative 3 up here. That results. Negative 1 times 3 is negative 3. Add those. 5 plus negative 3 is 2. Okay? And notice there's nothing left to do. Right? There's no more stuff to work with. So that last thing, since we're done, that is now our remainder. Okay? That 5 plus negative 3 gives us 2. There's nothing left to do with that 2. So that is going to be our remainder. So this is where I was saying now we have to take this and interpret it, okay? We're always going to have remainder here, and then from there, it just counts up in powers of x. So this is our remainder, this is our constant term, this is our x term, okay? If it kept going, we would have an x squared term and an x cubed. We obviously don't have those here, but now we know that our quotient is just 1x plus 3, okay? So we know that the coefficients of our quotient are just 1 and 3, and that the remainder is 2, meaning that we have x plus 3 as our quotient with a remainder of 2. So as a division statement, we have x squared plus 4x plus 5 over x plus 1. That's what we started with, remember, right? That's where this 1, 4, and 5 came from. 1x squared plus 4x plus 5. And this negative 1 came from the fact that for x minus a here, our a would be negative 1. And our quotient was a 1 and a 3. Now those are our coefficients, counting up in powers of x, starting from the constant term. So constant term is 3, and our x term is 1, has a coefficient of 1, I should say. So x plus 3, and then a remainder of 2. Okay, so it's the exact same answer we got when we performed long division. Don't believe me? Here they are side by side, right? Long division, we got a quotient of x plus 3 with a remainder of 2. Synthetic division, as long as we know how to read this, we can say, okay, remainder of 2, constant term 3, coefficient on x is 1. So x plus 3 with a remainder of 2. Okay, now, super important note. I referenced it earlier, but we didn't have to do it in that example. Sometimes we do. When doing synthetic division, we must write the terms of the dividend in order of descending power. We already said that. We have to do standard form, okay? But you must also use 0 for the coefficient of any missing powers. If you forget to do that, you'll get the wrong answer, okay? So what I mean by that is the algorithm for synthetic division, it is set up to work as long as every single power is represented there, okay? Meaning that it thinks this is the constant, this is the x term, this is the x squared term, which is correct for that one, right? But what if this was supposed to be, you know, x cubed plus 4x squared plus 5x, right? It actually wouldn't know. It wouldn't do it correctly, because it would still treat this. If I just did 1, 4, 5 for that, it would say, all right, x squared, x, and constant, okay? What I would need to do is add in a 0 there to tell it that this is actually x cubed, this is x squared, this is x, and there is no constant, okay? So we have to fill in the gaps with zeros if there are gaps. So let's try it out. For example, x to the power of 5 plus 7x squared plus 3x, if I wanted to divide that by x plus 1, how would I set it up? Well, my x minus a, right? Again, our a is negative 1, so I'd put a negative 1 here, okay? And if I just go and I look at this and I say, all right, 173. So this is not right. Don't write this. 173. It doesn't know. The algorithm is not set up to work this way. What it thinks I'm trying to divide by now is x squared plus 7x plus 3. Well, that's not our polynomial at all, right? So how do we tell it that this is supposed to be x to the 5th, 7x squared plus 3x? We just put in zeros where they belong, right? So x to the power of 5 plus 7x squared plus 3x, you could think of that like this. It's like x to the 5th plus 0x to the 4th plus 0x to the 3rd plus 7x squared plus 3x, and then we need that constant there too, so plus 0. So see what I mean? This is missing an x to the 4th, an x to the 3rd, and a constant term. Okay, the synthetic division algorithm doesn't work when we have left terms out. It just assumes, based on how many you wrote there, it assumes that's every exponent, every term, okay? So it won't know that this is supposed to be x to the 5th, okay, unless we tell it by putting in those zeros. So I would think of this as this, first. Okay, then we can say it's 1, 0, 0, and now it knows it knows that, okay, this is the next lowest power of x and the next lowest power of x. Then a 7, then a 3, then a 0. Okay, that would now be set up to work correctly. We could now do synthetic division on that because now it knows that, all right, this is the constant. This is the x. This is the x squared. This is the x cubed. This is the x to the fourth. And this is the x to the fifth. So this is now set up to work correctly. Let's try this out with a couple examples. It's quite fun, actually. I like synthetic division. All right, so let's try this out. First thing I notice, not in standard form. Also checking, looks like it is missing one of the terms, right? It doesn't have an x term, which is fine, but we need to put that in as a 0x to our synthetic division. So let's just first write this in standard form with zeros in for the missing terms. So I'll have 7x cubed, okay, highest power of x first, plus x squared is the next one. And then we've got a plus 3, but in between that would normally be an x term, right? Maybe not normally, but we have to say 0x plus 3. Okay, that's in standard form with our zeros in for the terms that have coefficients of 0. So that's what we're really doing, okay? And now we're ready to set up our synthetic division. So I'm going to go like this, okay? Our x minus a is x plus 3. So what's like the a that I put over here, that 0? Well, it's negative 3, right? If x minus a is x plus 3, then our a must be negative 3. Again, I'm calling it a 0 because we'll start to see in the next lesson that that would make, if this is a factor, the negative 3 would make our function equal 0. Okay? All right. Now I'll fill in the coefficients. Okay, so just the coefficients. That's the nice thing here. We keep it nice and simple. So I'm just going to put in a 7. A 1 is the coefficient on x squared. Don't forget the 0. We need to have that 0 there. Otherwise, it's going to think this is a squared, this is an x, and this is a constant. So I need to put that 0 there. And then my constant is 3, right? So my coefficients are just 7, 1, 0, 3. 7, 1, 0, 3. And here we go. Let's actually do the process. So first, we just bring down the 7. So I'm going to bring down the 7. Okay. Now I multiply. So negative 3 times 7 is negative 21. That goes up here. And now I just add down that column. So 1 plus negative 21 is going to be negative 20. Okay. 1 plus negative 21 is negative 20. And then I do negative 3 times negative 20. Well, that's positive 60. And now I just add 0 plus 60 is 60. And one more time, I'm going to multiply negative 3 by 60 to get negative 180. And I finish off by adding 3 and negative 180 to get negative 177. Okay, so again, we have to know how to interpret this now. That last one, that's our remainder, okay? Which means these represent the coefficients of my quotient, okay? And it always starts from, again, remainder, and then constant, the x term, the x squared term, right? If there was another one, it would be the x cubed, the x to the fourth, and on, but it stops at 3 here. So my quotient, these represent the coefficients on the quotient, okay? So our quotient is 7x squared, right? Minus 20x plus 60 as the constant term, okay? That is our quotient, Q of x. Our remainder is negative 177. So if we wanted to write a division statement, right? What did we divide? We took our dividend, So we did x squared plus 7x cubed plus 3. We divided it by our divisor, x plus 3. And that was equal to, so we found that our quotient was 7x squared minus 20x plus 60. And then if we add our remainder over our divisor, well, our remainder was negative 177. So I guess we could say subtract 177 over our divisor, x plus 3. And there it is as a division statement. Okay, if we wanted to check our work, which I think in the filled in notes I did do the whole checking of the work. In the interest of time here, I might not quite do it. But if you multiply this by x plus 3, what should you get? You should get x squared plus 7x cubed plus 3. And you will, right? I can confirm I did it in the filled in notes. You can go check those filled in notes and see where I did it. Okay, if I multiply this by x plus 3 and this by x plus 3, I end up with the original dividend. Alrighty, and last example here in the notes, let's go ahead and divide this one by synthetic division. So I'm going to set it up. I guess first I should check, is it in standard form? Oh, it is. Are there any missing exponents? Are any exponents not represented here because their coefficient is 0? Oh, there's actually not, right? X cubed, x squared, x, and constant. So this one's already set up nicely for us. Okay, so I'm actually ready to jump in and just start setting up my long division. Okay, so remember x minus a is our binomial divisor. So what's a here? Good, it's just positive 3, right? Our a is positive 3. And then I'm just going to use the coefficients of the dividend. So 2, 3, negative 4, and 15. Careful about missing negatives. You don't want to do that. So 2, 3, negative 4, and positive 15. Okay, and now we just get going. So I'm going to bring down the 2, bring it down. That's 2. Okay, maybe I'll be consistent with my color coding. 2. Now I multiply, so 3 times 2 is 6. Add down the columns. 3 plus 6 is 9. And we just keep repeating, making our way down this until we hit the end. 3 times 9 is 27. Negative 4 plus 27 is 23. Multiply 3 by 23 to get 69. And almost done. Add them up. 15 plus 69 is 84. And so we're done. That must be our remainder. Okay, so our remainder is 84. And these now tell me the coefficients of our quotient, q of x. Okay, so what is q of x? Again, the drawback to synthetic division is that we've got to, understand what this represents. So it's always going to go remainder, constant term, x squared term. Again, if it kept going, x cubed, x to the 4th term. But this is just going to be a quadratic. So it's going to be 2x squared plus 9x plus 23. That's our quotient. Our remainder is 84. So as a division statement, we would have dividend over divisor. So 2x cubed plus 3x squared minus 4x plus 15 over divisor. What were we dividing by? We were dividing by x minus 3. And we found that that was equal to 2x squared plus 9x plus 23. And then add our remainder. Remainder was 84 over x minus 3. Okay, and there we go. That's the answer as a division statement. Sometimes it just asks us for the quotient. Sometimes it asks for the division statement. It didn't really ask us specifically for one there, so I gave the division statement. Okay, I think these examples just ask you for the quotient. Okay, and again, how could we check our work here? We could, if I multiply, this is the result of dividing by x minus 3. So if I undo that by multiplying it by x minus 3, I should get this out. Okay, again, you can check the filled in notes. I actually do that, and you can see that it works out. If I multiply this stuff by x minus 3, I do end up with our original dividend polynomial. Okay, so go ahead and give these a shot. Some practice with the long division and the synthetic division. Give both, a fair chance, just so you're at least comfortable with the long division. I'll be honest, especially as we move forward into multi-step ones, we do rely on synthetic division a little bit more because it's quicker, okay? But worth a shot to get used to long division as well, because again, that's what synthetic division is based on. It's just an optimization of that process. Okay, so go ahead, try these out. Try the other practice questions for this lesson that you might not have done yet. Don't forget, as always, don't be shy to reach out to me or book an appointment if you've got some questions or stuff you want to go over or questions you got stuck on, whatever it might be. But there we go. That's lesson 1 of Unit 2.